let's dive right into this explainer. Today, we're totally unpacking ISO4833, which is basically the exact step-by-step master recipe scientists use to count bacteria in our food. If you've ever found yourself wondering how we actually know our groceries are safe, well, it all comes down to this highly structured, internationally recognized lab test. We're going to break this down so clearly that even if you've literally never held a pipette in your life, you'll walk away knowing exactly how to perform this crucial test yourself. Let's get right into it.
So here's our recipe for today. 1. The food safety blueprint. 2. Prepping your lab ingredients. 3. The inoculation procedure. 4. Incubation, the waiting game. 5. Counting the microscopic colonies. And finally 6. Calculating your final results.
All right, part 1, the food safety blueprint.
Okay, so the absolute most crucial point to grasp right away is that we aren't just looking for any random thing under the microscope here. We are hunting for very specific microorganisms. Under the ISO 4833 standard, we're talking specifically about bacteria, yeast, and molds that successfully grow into visible, countable colonies under highly controlled aerobic conditions. Think of them as tiny, distinct dots that pop up right on your gel. Basically, we're creating this VIP environment where only certain microscopic guests are invited to thrive, just so we can accurately count them.
Moving right along to part 2, prepping your lab ingredients.
Picture yourself right at the lab bench, creating the nutrient-rich bed where our bacteria are going to grow. It's really just like cooking. Step 1, you dissolve your nutrients. That's yeast extract, enzymatic digestion of casein and glucose into 1,000 milliliters of water. Step 2, you add your agar to give it that firm, jelly-like consistency and bring it to a rolling boil so it completely dissolves. Step 3 is super important. Dial in the pH to exactly 7.0, measured at 25 degrees Celsius. And finally, step 4, you place this whole mixture into an autoclave, which is basically a heavy-duty scientific pressure cooker, and sterilize it at 121 degrees Celsius for exactly 15 minutes. That ensures you're starting with a totally blank canvas.
Now, there's a really cool twist to this recipe. If you're testing milk, cheese, or really any dairy product, your recipe needs a special tweak. You've got to add exactly 1.0 gram of skimmed milk powder per liter to your culture medium. But, and this is a big but, that powder absolutely must be free from any inhibitory substances. We add this because, well, dairy microbes are kind of picky. They like to grow in an environment that feels like home. This little addition ensures we actually get an accurate count.
So once your agar is perfectly sterilized, you can't just pour it right away. It's way too hot. You have to cool it down in a water bath to exactly 44 to 47 degrees Celsius. Why that incredibly precise window? Because it's the absolute sweet spot. If it's hotter than 47 degrees, you will literally boil and kill the very bacteria from your food sample that you're trying to count. But if it drops below 44 degrees, the agar starts solidifying and getting chunky before you can properly mix it.
Which brings us perfectly to part 3, the inoculation procedure.
This is where your physical lab technique truly shines. Using a sterile pipette, you drop exactly 1 milliliter of your liquid food sample right into a sterile petri dish. You'll also do this for your decimal dilutions. If you're not familiar, that just means mixing 1 part of your sample with 9 parts of a sterile liquid so your final bacteria count doesn't end up too crowded to actually see. Next, you pour 12 to 15 milliliters of your comfortably warm agar directly over the sample in the dish. Now comes the finesse. Gently rotate the dish flat on the table in a figure-8 pattern. This mixes your food sample evenly into its new jelly home. Finally, just let it sit perfectly flat on a cool surface to solidify.
But you gotta watch the clock here. We have a massive, absolutely critical rule. You have exactly 45 minutes on the clock from the moment you prep your initial food suspension to the moment you pour that warm agar into the dishes. If you take any longer than 45 minutes, the bacteria in your sample might actually start dying off or multiplying in the holding solution, which completely ruins the accuracy of your final count. Efficiency is everything.
All right, on to part 4, incubation, or as I like to call it, the waiting game.
You need to set your incubator to exactly 30 degrees Celsius, with a really tight tolerance of plus or minus just 1 degree. This isn't just a random number. It's the perfect, cozy environment to encourage specific mesofluffalic aerobic colonies, meaning bacteria that love moderate temperatures and breathe oxygen, to really multiply.
Now, at hour 0, you don't just shove the plates in, you actually have to flip them upside down. We invert them so any condensation that forms on the lid doesn't drip down and ruin our beautiful growing colonies. Also, you cannot stack them more than 6 dishes high, and those stacks need to be separated from each other and from the incubator walls. Why? Airflow. We need that 30-degree temperature to be perfectly even across every single dish. Once they're placed properly, you close the door and let them bake, totally undisturbed for a full 72 hours.
3 days later, we're at part 5, counting the microscopic colonies. Time for the harvest. This is where your attention to detail really matters. Here's your golden rule. You only select plates that have between 15 and 300 colonies. Fewer than 15 isn't statistically significant, and more than 300, way too crowded to be accurate. You'll place your dish on a counting base with an illuminated background and grab a magnifying lens. Look incredibly closely and count every single tiny pinpoint. But watch out for spreaders. Those are fast-growing colonies that spread out kind of like weeds. You just treat a spreading colony as one single colony, but if a spreader has overgrown more than a quarter of your dish, you literally have to throw that count out. It's basically ruined the whole neighborhood.
And finally, part 6, calculating your final results.
So we have our numbers, but how do we know if our technique was actually any good? Well, ISO 4833 has built-in quality control. We look at 2 metrics, repeatability and reproducibility. Repeatability tests you. If you, in the exact same lab, with the exact same equipment, test the same sample twice, the difference between your results shouldn't exceed 0.25 on a log 10 scale. Basically, your 2 counts need to be mathematically almost identical. Reproducibility is the bigger picture. If a completely different scientist in another lab tests your sample, their results shouldn't differ from yours by more than 0.45 on that same scale.
So if you're trying out this test for the very first time, this right here is your benchmark. You do the test, you do it again, and if your own results stay within that super tight 0.25 difference, congratulations! It means your pipetting was spot on, your temperature control was flawless, and your counting was sharp. You have officially mastered the microbiology MasterChef recipe.
The sheer precision of this ISO 43 standard is what keeps us safe every single day. From nailing the exact pH of the agar, to racing that 45-minute countdown, to the meticulous 72-hour incubation, it's just a beautifully designed protocol. What you should really take away from this is a profound appreciation for all that invisible, highly skilled work going on behind the scenes of our global food supply. So next time you take a bite of your favorite food, I want you to ask yourself, what invisible numbers did a technician meticulously count to put this safely on my plate?